diesel engines may be two-stroke or four-stroke and will generally be classified as slow speed, running at about 80 to 150 rpm, or medium speed, from about 250 to 750 rpm. High-speed diesels operating at greater than 1000 rpm are used in specialist craft and in certain coastal vessels, and are also used as power generators on vessels of all types. In all cases, turbocharging increases efficiency and power output. In general, it can be said that a two-stroke engine is more thermodynamically efficient than a four-stroke, but that a four-stroke requires less space for the same power output and allows greater flexibility of position within the ship. To operate at its maximum efficiency, there should be complete combustion of the fuel in the engine cylinders. To achieve this requires correct atomization of the fuel and precisely timed delivery into the cylinders. The size of droplets produced is affected by fuel oil viscosity, nozzle hole size, and the pressure difference between the injected fuel and the compressed air in the cylinder. If the injector nozzle is run at too high a temperature, deposits of carbon build up in a characteristic trumpet shape and affect the atomizing efficiency. The tendency for the fuel to form carbon deposits is indicated by the microcarbon residue, a measurement carried out in the laboratory and included in the fuel specification. The fuel spray pattern is governed by the number and position of the nozzle holes. Ideally, the droplet should penetrate the whole of the combustion space for good fuel-air mixing, but should not impinge on internal surfaces before burning, as this could lead to excessive liner wall temperatures, removal of the thin lubricating film of oil, and possible cracking of the liner. The burning of the fuel can be considered in three stages. The first stage, the ignition delay, starts with the fuel injection. The droplets mix with the hot air to produce a vapour cloud, and at the correct temperature, usually above 500 degrees Celsius, combustion occurs spontaneously. In the second, pre-mixed combustion stage, the temperature rises rapidly to produce more vapour and trigger off other combustion sites. The flame front propagates through the cylinder, burning all the other droplets present and generating a rapid rise in pressure. In the third, diffusion combustion stage, the existing and new combustion products start to slow down the combustion process. Turbocharging is commonly used to force more air into the cylinder prior to combustion, allowing a greater quantity of fuel to be burnt, and so increasing the power output. Air-to-fuel ratios of 30 to 1 are common. The charge air cooler, by making the air more dense, allows an even greater mass of air into the cylinder. The products of combustion are emitted to the atmosphere. The normal combustion products of hydrocarbons are water vapour and carbon dioxide, with their proportions varying very slightly according to the composition of the fuel. Almost all the nitrogen in the intake air passes through unreacted. Due to the excess air ratio, a large proportion of the free oxygen is also unmodified, so these two gases comprise the majority of the exhaust. Small amounts of carbon monoxide and the various oxides of sulfur and nitrogen will be present in the exhaust. The level of sulfur oxides depends largely on the sulfur content of the fuel. The various nitrogen oxides are affected by the combustion properties of the engine and often increase with efficiency of combustion. Environmental concerns will soon lead to the introduction of MARPOL Annex 6, requiring new designs of engines to address these problems, and will probably include the catalytic reduction of emissions. Small quantities of hydrocarbons in the exhaust will consist of unburnt or partially burnt fuel oil and lubricating oil. This portion may embrace a huge range of organic compounds which could be present in vapour or particulate form. Other particulates would be inorganic substances such as carbon, ash minerals and heavy metals. These 5 categories all have potentially harmful effects on human health and the environment. Sulphur in the fuel, which can be as high as 5% by weight, may combine with water to form sulphuric acid, which, if present at a temperature less than its dew point, will condense on the cylinder liner and attack its surface. Marine fuels are usually the heavy residues of crude oil after the refinery has removed lighter distillates, and often different residues are blended. It is important to keep bunkers from different sources in separate tanks. Vanadium, or sodium, in the fuel encourages the formation of deposits which build up around the exhaust valve seats and might lead to failure of the valve. High quantities of aluminium trioxide or silicon dioxide, highly abrasive materials which are used in the oil refinery as catalysts, can lead to rapid damage to the fuel pumps, the injectors, piston rings, pistons and liners. The aim of sampling is to obtain a representative specimen for the whole bunker, and the preferred procedure is the continuous drip system, which samples the fuel throughout the entire delivery. An automatic quality level, or AQL sampler, which should be sealed against tampering, enables 3 1-litre bottles to be filled flow proportionately throughout the batch. After delivery, a ship's representative should witness the labelling and sealing of the sample bottles. One is retained by the ship for at least 3 months. One by the bunker barge. Many owners dispatch the third to an officially recognised testing agency. At the testing laboratory, full analysis of the fuel is performed to the current international marine fuel standard ISO 8217, providing information which can be of real relevance in the running of the engine. A fuel is said to be unstable if its components break down before or after aging. For test purposes, the aging process can be accelerated by the addition of a chemical and heating the sample at 100 degrees Celsius for an hour. If the sample then produces deposits, it is a sign that the fuel could do the same on the ship, blocking the fuel filters and presenting the danger of breaking down the lubricating oil film on the cylinder liners. Water content is measured by a distillation process. Toluene is added to the sample and the mixture heated. The toluene and water boil and evaporate together. When condensed, the toluene separates from the water, which is collected in a glass trap. Sulphur content is a relatively quick test to perform once the machine is fully calibrated. Pour point requires cooling of the sample at a specified rate and constant checking for its fluidity. Flash point is the lowest temperature at which the fuel's vapour will ignite. The sample is heated slowly in a sealed container. Vapour builds up and is tested every 1 degree Celsius, and at the flash point is seen to ignite. Marine fuels are priced according to kinematic viscosity, which is a measure of fuel flow under gravity. The test involves precise timing of the sample's passage through a narrow tube. In the analysis for carbon residue, carefully weighed samples are lowered into a furnace and heated to 500 degrees Celsius. The amount of residue produced by a fuel indicates its tendency to form carbonaceous deposits in the engine. The most sophisticated analysis is that which detects elements in the fuel such as vanadium, sodium, aluminium and silicon. At the start of the process, the sample is ignited to remove all combustible components, the majority of the fuel. Then, 6 hours in a high-temperature furnace removes the remaining carbon in the form of carbon dioxide, leaving just the elements. The sample, now in solution, is analysed by a process known as inductively coupled plasma emission spectroscopy, or ICPES. The instrument uses argon plasma at 10,000 degrees Celsius. At this temperature, all the elements emit characteristic spectra. These are measured accurately, and the results appear on the computer screen showing the progress of the analysis. Every component of the fuel has now been measured, and the results are faxed or emailed back to the ship. All residual oils are likely to contain contaminants of some kind which must be reduced or removed to protect the engine. Contaminated oil might contain fresh or salt water which will promote corrosion. Thus, the first treatment, in the storage tanks, is for the fuel oil to be heated. It will also be heated on transfer to the settling tank, allowing some of the water and sludge to settle out by gravity and be drained off. Solid contaminants could include particles of rust, sand, dust, and catalytic fines from the refinery. These are all abrasive and will cause wear. To remove these, 2 centrifuges usually operate in series: the purifier, which removes more water, solubles and sludge, and the clarifier, which removes fine solid particles. After purification, the fuel is held in the service or daily tank, which is also heated, and from there onwards it flows under pressure to inhibit boiling or cavitation. The supply pumps raise the pressure to about 4 bar, and the circulating pumps to about 12 bar. Then a heater raises the temperature again, its action being controlled by a viscosity regulator. It is essential for the fuel's viscosity to be lowered for correct atomization in the cylinder. The fuel passes through a fine filter to remove particles larger than 50 microns, and is finally delivered to the engine's fuel pumps, which raise the pressure to over 300 bar for injection into the cylinders. Proper running of the engine is indicated by a wide variety of measured parameters: the inlet fuel temperature, exhaust gas temperature, the peak pressure, the cylinder compression pressure, cooling water return temperature, the lube oil return temperature, turbocharger gas temperature, turbocharger speed, and turbocharger inlet and outlet gas pressures, all of which will be defined in the manufacturer's manuals. But the most significant information relates to what is happening within the cylinder. Starting from bottom dead center on the compression stroke, the volume of air in the cylinder is at its maximum and its pressure is fractionally above atmospheric. As the piston rises and the scavenge and exhaust ports, or valve, closes, the air within the cylinder is compressed, its volume decreasing and its pressure starting to rise. This is the same for both the 2-stroke and the 4-stroke cycles. As the piston approaches top dead center, the air's volume is reaching its minimum. The fuel is injected, and as it ignites, there is a sudden increase in pressure. The piston is forced downwards, with the interior gases now increasing in volume and declining in pressure. The exhaust ports or valve opens again, and the pressure drops to the minimum. The four-stroke cycle is similar, except that on the additional two strokes, the exhaust and induction strokes, the volume of gas changes, but its pressure hardly does so. This graph is known as an indicator diagram and tells us much about the performance of the engine. For a start, the area within the curve is a measure of the power produced in that cylinder, and this provides a method of balancing the different units in an engine. The traditional way to obtain such a diagram is with an engine indicator. It uses pressure-sensitive paper wound around a drum. A horizontal trace represents atmospheric pressure. Each of the engine cylinders has an indicator cock which must be kept well maintained and clean to ensure reliable readings. The cock is opened to blow out any carbon deposits. The indicator is screwed onto the cock and its internal piston moves against the spring according to the pressure in the cylinder. The cord, connected to one of the engine's cams, rotates the drum according to the piston's position. The traced-out curve relates pressure to volume at any moment in the cycle. Taking an indicator card, with the fuel to the cylinder shut off, produces the compression diagram. The height of this curve is the maximum compression pressure, and low compression would indicate a worn liner, faulty piston rings, insufficient scavenge air, or a leaky exhaust valve. Another diagram is the draw card or out-of-phase diagram. The fuel pump is engaged, but the indicator drum is set 90 degrees out of phase with the piston stroke. A competent engineer can produce a draw card by pulling the cord of the drum by hand. The diagram shows more clearly the changes in pressure during combustion and will help reveal fuel timing and injector faults. A deviation like this indicates fuel injection is early. There is an abnormally high peak pressure at the top of the piston stroke. This might be accompanied by a knocking sound. If the curve deviates like this, it indicates late fuel injection. The peak pressure is low and occurs well after top dead centre. Slow or late combustion, known as afterburning, raises the pressure during the expansion stroke, so the line deviates like this. This would be accompanied by high exhaust temperatures and pressures, with a possible fouling of the exhaust system and the breakdown of lubrication in the cylinder. A leaking fuel injector produces a jagged line indicating fluctuations in pressure due to secondary burning, and if the jagged appearance applies to both sides of peak pressure, it indicates a partly choked fuel injector. Indicator cards should only be taken when the ship's progress is stable and there are no planned changes of course. If indicator cards taken from all the units diverge from normal, they point to a general faulty condition such as fuel quality, the fuel quantity injected into each cylinder, the turbocharger, engine cooling, or incorrect camshaft timing. For engines running at greater than 100 RPM, there is too much vibration for an indicator card to be taken, but nonetheless, a peak pressure reading also provides a good indication of the power being produced. The traditional indicator equipment is being replaced by electronic equipment, which provides the same functions on engines of any speed. The diagrams produced are the same and indicate the same faults.
Chief.
Hello.
Seems to me as smoke's going black. It was clear yesterday.
Really? Then have a look at the temperatures. Nothing wrong there. How dark was it?
Pretty black, Chief.
Oh. How's the viscosity? That's all right. Right. Well, This is the grade of fuel we're using, so the inlet temperature should be 120 degrees. I'm going to check it. Well, that's okay. Well, what else could it be?
Could it be the scavenge jet pressure?
Yeah, you could be right. Oh, that's okay. Turbocharger revs? Okay too. Right. We ought to check the pressure drops across the air filter and the air cooler.
Right.
Right, let's have another look at the lab report. If there was a lot of aluminium or silicon, they could produce wear quite quickly in the fuel pumps or injectors, but they're normal. What about carbon? That's okay too. Well, that leaves the timing.
You have to take some indicator cards.
Absolutely right.
All of them?
Yep. Oh, there you are. You see? The injection's late. We'll have to adjust the fuel pump timings when we get to port.
Excuse me, Chief.
Yeah,
Number 4 unit, its exhaust temperature is too high.
it's always run a bit high. I shouldn't worry.
80 degrees is too much, Chief.
80? 80 above normal?
Yes, Chief.
That is a bit hot. Let's go and check the local gauge. Well, both gauges are showing it's running too hot. Let's go and check the rack settings. Well, the rack settings are all okay. We'll check the turbo revs. Turbo revs are okay. We ought to check the compression pressure.
Indicator card?
Exactly. It'll show us if there's a valve leaking or if the rings are worn. Compression pressure's fine. Timing's fine. This is a tricky one. I think we're going to have to take a look inside. Yeah, it's Aaron here. Is the captain available? Captain, it's Aaron. We've got one of the cylinders running very hot. Checked everything we can with the engine running. We're going to have to take a look inside. How soon will we be alongside? Okay, that should be fine. No, hopefully it'll only take about an hour. Okay. See how it dribbles? That's well worn.
All the components of a diesel engine start their life in sound condition, but if it is not run correctly, they could be subject to carbon build-up, to cavitation, to wasting due to escaping exhaust gases, to excessive internal pressures causing cracking, to damage due to incorrect running temperatures or due to dirty fuel, to impact damage caused by broken-off fragments of piston ring or exhaust valve. Specialist engineering firms can return many components to their original condition by regrinding needle valves and seats and retesting atomization, by rebalancing turbocharger components, and by accurately measuring the quantity of fuel delivered by a pump at any particular rack setting. Running the engine plant efficiently reduces the need for such work, keeping to regular maintenance and inspection schedules, which will have been published by your company and by the manufacturers of all the principal items of diesel equipment, is extremely important. Carefully monitoring your engine's fuel quality, as well as the conditions inside each cylinder, will result in the engine running cleanly, reliably, and economically.